So recording last time. Okay, so we're covering Facebook. We'll do the first half of it. We'll talk about system scale, big data, and capacity, and we'll talk about different kinds of memory, volatile and non-volatile. Okay, so Facebook is really big, as everyone knows, billions of monthly users, well over a billion regular daily users, and there aren't that many new people joining the internet anymore. So at this point, you're on Facebook because your friends are on there, and even if some new platform comes along that's better than Facebook, people just aren't going to join it. Hold on. People aren't going to join Facebook because people aren't going to join the competitor because there are not that many new people joining the internet. People are already embedded in Facebook. Facebook could really have to drop the ball, like have some major security failure or something to get people to go away. So having said that, Facebook's not invulnerable. If there were huge annoyances like really slow page loads, that could drive people elsewhere, or competitors might do something a whole lot better than Facebook's current model. Things like a better interface, fewer constraints on data, better privacy, better security. It's possible. It's unlikely for the foreseeable future, but you never know. So right now, Facebook is so big, it's really hard for another competitor to come along and make a major dent in Facebook's model. Right? Other companies have tried for a little while. Google was trying to do a serious social media competition to Facebook, but it just didn't take off. But having said that, still Facebook needs to keep continuously innovating to manage its huge and growing scale. Facebook is really big. Operating a big operation the size of Facebook is a difficult thing. And so they have to keep up with that. Otherwise, they might end up going the way of MySpace. Okay. So as you might know, Facebook's the world's largest social media application, very, very large. You don't need to memorize these numbers because this is not a trivia contest. Okay, I'm not going to ask you about these specific things on exams, but just have an idea that it's very big, right? Billions of regular users, 350 million photos uploaded daily, so something around the order of at least an exabyte of photo data every year. And the annual ad revenue they get these days is about 70 billion a year. So very big operation. And the consequence, things that are simple on Facebook, things that are simple at small scale require specialized systems for Facebook, okay? So give an example. Anybody know off the top of their head what the largest number of rows you can have in an Excel document is? Anybody want to guess? Oh, we got some guesses. Let's see. I'm going to stop the, oh, there we go. Oh, we have some good guesses in here. The actual number is just over 1 million. Just over 1 million. So yeah, you can do it. Okay, you can get a very large thing. So we'll get back to the, slides. That's fine. Okay. So you can have a pretty large Excel document of 1 million records, all right, 1 million rows. Now, if you're an ordinary small business and say you want to use Excel to keep track of your list of customers, there's no problem with that, right? You're not going to hit 1 million anytime soon. But if you're Facebook and you have billions of users, you can't just do that in an ordinary Excel document. You either need some very specialized spreadsheet equipment or you need some massively parallel version of Excel. You got to do something different, right? So again, things that are simple for a small operation require extra work for Facebook because it's so big, right? Similarly, if you're looking for a file on your own machine, right, you can just click on the folders and do a quick search in there and it'll scan your directory and it will eventually find the file you're looking for. Now, if you have an old computer with a lot of files on it, it could take several minutes to scan through all of that and find the file you're looking for. Well, Facebook obviously has a whole lot more data than that. It has literally billions of times more data than, what am I thinking of? Then can be stored, well, billions, terabyte, exabyte, literally millions of times more data than you're going to store on one single computer. So they can't do it that way, right? If they have to search their entire system, all of them, every time they're trying to find a file, no, it's just going to take way, way too long. So they have to have a much better index system, a much better way of retrieving files. So like I said, one of the things with scale, the good side is Once you get big, if you're able to manage the challenges of scale successfully, it's difficult for competitors to break in. But managing the challenges of scale is not a trivial thing. Okay, moving on. So quick thing, scale measures, these are things you should know just to have a working idea of all the terms we're talking about. So kilo, mega, giga, tera, those are all ones you experience in everyday usage. So a kilobyte is 1,000 bytes, so about a page worth of data, right? A short text file. Mega is 1,000,000, and a reasonably large image would be a megabyte of data. Giga, right, is 1,000,000,000, so a gigabyte is 1,000,000,000 bytes, and roughly speaking, about a long video. So the maximum capacity on a CD, a compact disc, was about 0.66 gigabytes. The data on a DVD was about 1.3 gigabytes. So if you can fit it on a DVD, it's probably about a gigabyte. A terabyte, on the other hand, these days is about a typical size for a hard drive. So that's what a terabyte is. You can hold a lot of videos on one hard drive. Petabyte, exabytes, and zettabytes, those are things that we probably don't have in our everyday experience, unless you work for one of these big tech outfits. So a petabyte, if you want a rough number on that, 1,000 hard drives worth of data, which is roughly equivalent to all of Facebook's new data, right? So all the photos that get uploaded to Facebook over the course of the day, that could be about a petabyte, probably on a slow day these days. An exabyte is 1,000 petabytes, or 1,000,000 terabytes, so 1,000,000 hard drives. And that's a good number for all the data of a large business. Now, your big operations like Amazon, Facebook, Google, they have many exabytes of data, probably less than 100, maybe more, but they have a lot of data, way more than 1 exabyte, okay? And last one, the zettabyte. The zettabyte is an amount equal to about the total internet traffic. These days, total internet traffic is about 4 zettabytes. It was a few years back that we entered the so-called zettabyte era, where we crossed the 1 zettabyte for internet traffic in a year. But yeah, these days it's about 4 or 5. It'll probably be close to 5 by the end of the year if we go backwards with a floating window, okay? So you should know what those prefixes are, what they stand for, how they relate to each other. If you like, you can probably come up with some snappy mnemonic to remember it. Something like, what did I used to do? I don't know. Kill many giraffes through poisoned eating zebras. I don't know. Figure out something. Make it work. I don't know. Okay, but you should know the first 4 already, and then all you got to remember is peta, exa, and zetta. And zetta should really be easy to remember because Z is the last letter of the alphabet, and it's the last one in the list. So, all right. Now, next thing, big data. So big data is still a widely used term, even though you shouldn't use it. We'll talk about that in a minute. Big data is a widely used term, but what exactly does it mean? Well, part of the problem with it is it's inherently imprecise, it's inherently technology dependent. What it means in real terms is if your amount of data becomes difficult to handle with standard off-the-shelf systems or software, okay? So, for example, something that UIC would consider big data is going to be really trivial for Facebook, right? Facebook manages much, much more data than UIC does. Likewise, something that's big data for 2000 is pretty trivial for 2020. There's a typo in there. I'll have to fix the slides. So, yeah, I remember when I first moved to Chicago, I got my first desktop in 1998. It was running Windows XP. And it had a hard drive that had an unthinkably large 6 gigabyte capacity. At the time, I thought, wow, 6 gigabytes, I'm never going to fill up all that. And in fact, I never did. I got about halfway. So it was kind of in the pre-video era, and that's where all the real data went those days. But 3 gigabytes, 6 gigabytes in those days was a lot of data. But now, a few gigs of data, no, that's nothing. It takes a few seconds to transfer from one machine to another. You can carry it around on a, on a thumb drive. It's very easy. Back in those days, back in 2000, we had floppy disks, 3.5-inch disks that carried, just a couple megs. So if you had a gigabyte of data, that could take you, 500 floppy disks to put on. So that would be a big hassle. Okay, so the definition of big data changes over time. But again, as a working definition, big data just means that it requires some kind of special tool or system to manage. The problem with saying big data, number one, it's kind of a buzzword that's been overused. And number two, it's inherently vague. So you can say you have a big data problem and people guess, oh, yeah, you're not able to manage all the data you have. But it's much better to be more precise. For example, you could say we have too much data. We have a volume problem. We are running out of space to store it in. Or it's difficult to extract the data that we have because it's so big. Our indexing system is not efficient enough. Velocity, it might be arriving too quickly. There's too much changeover in our system, and that's causing problems with us. Variety, you have different types of data, right? Maybe you have problems because some of your data is very compact and some of it is very large, like you're trying to store images and videos in the same system. That can be a problem. And veracity, which is a fancy word for truth, right? Basically, once you have a lot of data, it becomes much more difficult to verify through cross-checking that all of it is actually correct. So if you have multiple copies of data, you're going to have to exert more and more effort over time to ensure that it's all correct and up to date and none of it's been corrupted, that sort of thing. Okay, so if you're interested, I have a link to a little picture there, talks about some more stuff. But right now, I'm going to do a quick pause and see if people have questions, and we'll go from there. So I'm going to pause. Okay, so here we are resuming. Okay, back to our slideshow. All right, so don't say big data. That's the key takeaway from all this. You can talk about different types of data problems, but if you just say big data, we have a big data problem, then people are going to kind of look at you funny. Okay, now Facebook, when they put a photo on Facebook, it's a fairly complex multi-step process. So what's going to happen, you know, for when we do it, we just upload it and we don't have to worry about much of the rest. But Facebook has to do a bunch of stuff. It has to accept the upload, figure out where it's going to store it. It has to scan it for prohibited content. It has to store and replicate the image. So it has to figure out what data center it's going to store it at. It has to make multiple copies of it. And then it's going to have to distribute it to other users. You know, anytime you upload something on Facebook, your friends are going to get a notification, so-and-so posted a photo. So the ability to do those steps quickly at scale is a key part of Facebook's competitive advantage, right? The fact that Facebook is really big and can conduct these operations very quickly, that's what keeps people coming back to Facebook. Okay, so basic capacity problem. Facebook has to match supply and demand for aggregate user actions. What does that mean? Well, the supply is how much capacity Facebook has to handle photo uploads. The demand is how many uploads people want to make, right? So if Facebook has a lot of extra supply, they're wasting money. They have a bigger system than what they need. On the other hand, if they're less than demand, then people are going to have to wait and people are going to get displeased. So what are the things there? Well, demand can be influenced, but it can't be controlled. So Facebook can do little tweaks to try to encourage people to upload photos at different times of the day. But at the end of the day, Facebook can't simply say to users, you only get to upload 1 or 2 photos a day, or you have, a 1-hour time slot where you can upload photos, because people aren't going to like that. They're going to react negatively to that. So Facebook is going to let people do whatever they want, and it's going to have to put in some extra slack in its system, some extra capacity for when things get busy. So the supply attributes, that depends on the hardware, right? How fast the hardware is. So for example, if you're doing solid state drives, that's going to be faster than your regular hard disks, right? Your mechanical ones. So hardware matters, and then the process design matters. And Haystack is essentially a big change in the process design that Facebook implemented. So however your system is, it's going to cost so much, and you can try to do the best job you can providing a system with capacity X. But if the requirements go up, you're going to have to pay more for that. At the very least, you're going to have to pay more for additional storage capacity. Now, here we get into a little tiny bit of math. It's not real math because we're not going to do any numbers, but I'm going to express this whole concept as an equation. So over time, Facebook's processing capacity has to meet the photo upload rate. So if we're going to write that as an equation, we have lambda here. Lambda is the lowercase Greek L on the left, equals S divided by T sub P. So lambda is the photo upload rate. So in statistics, lambda is commonly used as an arrival rate, the rate at which things happen. So however many photos people are trying to upload to Facebook, what that can manage, how many Facebook can manage is the number of system processors, right? So however many servers Facebook has for processing photos, and T sub P, the time to process each photo. So if Facebook adds more servers, S goes up, and then the left side of the equation, the lambda can go up. Facebook can handle more photo uploads. Likewise, if T sub P goes down, because Facebook is able to process photos faster, then the quantity on the right will also go up, and so lambda can go up, right? So the two ways to manage this issue, you can either add more machines, or you can streamline your process somehow, get faster machines or a better system. And either way of those, you can increase the supportable photo upload rate. So what has to happen if the upload rate increases? Either you need more processors, you got to shorten the processing time, or there's going to be a backlog, right? And Facebook really does not want a big backlog of photo uploads because that makes people unhappy. And unhappy people don't come back to Facebook and help Facebook make money. Okay. Now, Facebook's solution, very simplified version we're giving today, we'll talk more about it on Tuesday, has a giant system that combines RAM and permanent storage. So the most popular requests are cached in RAM. That just means caching is a fancy term meaning easier to get to. So they're cached in RAM for quick access. And then they're also replicated for reliability. Facebook typically makes a triple copy at least of any photo that's been uploaded. So the most popular photos are stored in RAM so they can be accessed quickly. Other ones are still able to be accessed quickly enough. The name of this system is called Haystack, from the old metaphor, I guess, of finding a needle in a haystack, which is like finding one photo in Facebook's massive storage system. A couple of links there if you want to check those out, but those will probably make more sense after we talk about Haystack on Tuesday. So, but before we can really understand Facebook's solution, we need to know more about memory and databases. So we're going to cover some of that. Now, the two basic flavors of memory are readable, read-only, or read and write. So read and write means you can change the values that are in there. So think, for example, of a piece of paper as a piece of memory. If you have a piece of paper, you can read from that. You can also write over it, right? You can erase what's on there and write something new. So that's readable and writable. You can change it. On the other hand, if it's read-only, that means you can't change what's on there. For example, somebody is trying to enter the room listed as Gas's ass. I am going to decline that one. I'm not going to let somebody enter in with that room. You can, Mr. Gas ass. No, we're not going to do that today. Okay. Anyway, so read only means you can only read from it. You can't actually change what's there. For example, chiseling something in stone, right, is pretty much there forever, or burning a piece of plastic with a laser. Okay, we got some guy in a skull mask flipping me off, or flipping somebody off. So we are going to boot him. Bye-bye. Okay. That was strange. Anyway, the other two, within the umbrella of read and write, within the realm of read and write memory, you have volatile and non-volatile. So non-volatile memory means things that don't change when the power goes away. Volatile memory means the memory is lost when the power goes away. So essentially what happens in RAM, you have a bunch of switches inside that store the data that are held in place by the voltage being applied. When the voltage goes away because you unplug it or the battery disconnects or whatever, all those switches fall down into the zero position and the memory is lost. Non-volatile stuff like hard disks or flash memory, yeah, those things are more or less permanent. Okay, so those are your basic flavors of memory. Now, different access models, there's a few of them. So sequential access memory, those were mostly the first types of memory. So in sequential access, data gets accessed in a specified sequence. And generally that requires a fairly long seek delay to find the starting point. So a good example of that is a cassette tape, right? If you've ever seen one of those at your grandparents', whatever, you have to spool through the tape to find the exact place where you want to start reading data from, okay? So it takes a little while. Once upon a time, sequential access like tape drives were really cheap and slow. They were much cheaper than hard drives in terms of capacity. But these days they're not, because they aren't made in any kind of large quantity, and digital media is a lot cheaper. So they do still exist. You can still find tape drives for things like extreme conditions where like mechanical drives would break down from being bumped around. But yeah, generally sequential access memory is really slow, and for that reason, it's really hard to find. The next type is direct access storage devices. So direct access is a mix of sequential and indexed and direct access. What does that mean? Well, if you've ever played an old-timey vinyl record, you know that it is divided into tracks. And if you want to hear a particular song on the record, you move the needle to the particular track and you place it there, and it is what it is, right? You let it start playing. So anything you can start it on a new track, but then it's really hard to do a fine-tuned pointing to a particular portion of that track. Like if you just want to hear a particular thing in the middle of it, it's hard to get it right to that point. So generally you put it at the start of the track and you let it play through. And that's the way old hard drives worked, is they would have their surface divided up into tracks. Anytime you wanted to find something on there, they'd move the drive head to that position of that track and then scan through it to find the actual data within that track. So that's what we mean when we say a mix of sequential, indexed, and direct access. So it's sequential in the sense, once you move the drive head to a track, you got to scan through that track to find what you're looking for. And direct access is you can kind of go to the point where you're looking for. If you really want to optimize your hard drive, you can put the most important data at the start of any track. And then you need an index to find exactly which things are located on which tracks and where those tracks are positioned and such. So where you would see those is things like hard drives and optical drives like CDs, DVDs, that sort of thing. The last one is RAM. RAM stands for random access memory. And what makes it random access is that data is accessed in about the same time regardless of where it's located. Okay, if this were a computer engineering course, we'd have a lot of fun talking about multiplexing and stuff, but it's not, so we won't. Key takeaway is just RAM is faster. Because RAM can access stuff at the same speed and because it's all electronic, RAM is a lot faster than these other methods. But it's also generally much more expensive. So for example, if you want to talk about getting a terabyte of RAM, that would be at least several $1,000s. On the other hand, if you want to get a terabyte of hard drive storage capacity, that's maybe 40 bucks. So RAM is vastly more expensive than other types of media, but for some purposes, the speed is important. All right, so where we see RAM, things like main memory in a computer, what you just call the RAM in a computer, USB drives and solid state drives, they all use varying types of RAM. Okay, so the three key RAM subtypes: dynamic RAM. Dynamic RAM is cheap and obsolescent. You don't really see it anymore. Synchronous RAM is faster than ordinary dynamic RAM, but much more expensive. So dynamic RAM is basically obsolete. It was nice when we had it, but it's been about 15 years since you could actually buy a machine that had the original version of dynamic RAM. Synchronous RAM is just the same kind of idea, much faster. And what makes it synchronous RAM, essentially, anytime you're trying to send a message to RAM, you're sending electrical signals to the 8 switches in a given byte. So the window that it happens for those signals to arrive at the same time, that's what needs to be synchronized. If you can get all of those signals to arrive at the same time within a very short window, that means you can pack more different signals into a given amount of time. That's what allows the RAM to operate faster, because all of the switches get the data at the same time and everything can happen faster. So that's why they call it synchronous RAM. And the DDR level, so when you see it in a store, it'll be something like SDRAM-DD4 or DD5. Every higher DDR level means twice as fast as the generation before. So DDR5 is twice as fast as DDR4, which was twice as fast as DDR3, and so on. The last one, static RAM. So static RAM is very interesting. Unlike many types of RAM, whoops, wrong button there. Unlike many types of RAM, it does not require constant power. So it's faster, has less power consumption than DRAM. That's the advantage. It's actually blindingly fast. It can do things in less than a nanosecond, which is incredible. Where it's used is high performance CPU caches. So you have some extra memory attached to your CPU that if there are repetitive instructions, it can zip through them very, very, very quickly. There's two kinds of caches, L1 or L2 that are for a particular CPU or core, and L3 that's shared among a set of CPUs or cores. So the difference about static RAM, it's actually bulkier. It takes up more space than your regular synchronous RAM. So in very small quantities, like I said, it's blindingly fast, but in larger quantities, the fact that it's bigger means that size difference means it takes longer for the signals to get where they need to be. Okay. So this is a good point. We'll do a little Q&A here. We'll see how things are. I'll pause the recording.